Magnets are all around us. You'd be surprised to know that all known materials exert some sort of magnetic force, but it is so small that it is not readily noticeable. With other materials, it is much larger, and these are referred to as magnets. Magnets aren't just used to stick stuff on the fridge, they can be used to power MRIs and generate electricity, among other things. But how many types of magnets are there, and how are they made? There are a bunch of different magnet types. Some magnets, known as permanent magnets, exert a force on objects without any outside influence. The iron ore magnetite, also known as lodestone, is a natural permanent magnet. Other permanent magnets can be made by subjecting certain materials to a magnetic force. When the force is removed, these materials retain their own magnetic properties. Although the magnetic properties may change over time or at elevated temperatures, these materials are generally considered to be permanently magnetized, hence the name. There's yet another type of magnet called an electromagnet. They are made by surrounding certain materials with a coil of wire. When an electric current is passed through the coil, these materials exert a magnetic force. When the current is shut off, the magnetic force of these materials drops to nearly zero. Electromagnetic materials retain little, if any, magnetic properties without a flow of electric current in the coil. To make magnets from alloys, the first step involves selecting the appropriate raw materials. For alnicomagnets, the primary constituents are aluminum, nickel, and cobalt, with additional elements like copper, iron, and titanium. The precise proportions of these elements are crucial, as they determine the magnetic properties of the resulting alloy. Careful consideration and control of the alloy composition are necessary to achieve the desired magnetic strength and stability. The raw metals are cast into molds which define the shape of the magnet. These molds are usually made from sand, since it can withstand the high temperatures of the molten alloy without melting or deforming, and is cheap and readily available. The process begins by creating a sand mold of the magnet shapes. They load the pattern of magnet shapes into a machine that fills it with sand. Once the pattern is filled, it's removed from the machine and the surface is smoothened out, removing any excess sand from the top. Once this is done, the sand mold is placed in the machine again. This time though, the machine pumps in gases to chemically harden the sand. It takes just seconds to solidify. They lift out the sand slab, revealing the impression of the magnet pattern. It's now a mold. The casting process plays a pivotal role in determining the overall structure and composition of the magnet. It sets the foundation for subsequent steps, including heat treatment and machining. Next, it's time to mold the magnet shapes. They take copper, cobalt, sulfur, nickel, pure iron, aluminum, and titanium. These metals are placed in an induction furnace where temperatures can reach around 1600 to 1700 degrees Celsius or 2900 to 3100 degrees Fahrenheit, heating the metal into a molten mixture. Induction furnaces use electromagnetic induction to generate heat directly within the metal. They consist of a crucible where the raw materials are placed, surrounded by an induction coil. Magnetic field induces electric currents within the metal, leading to rapid and efficient melting. While heating, the homogenization of the molten alloy is crucial for ensuring that the different elements are evenly distributed, contributing to the uniformity of the magnetic properties throughout the final product. The molten mixture is then poured into the sand molds. If you're wondering why the sand has burst into flames, it's because the gases that were used to harden the sand previously are highly flammable. Following the casting process, the magnet undergoes a controlled cooling and solidification phase. For this purpose, the molds are slid into another part of the foundry and knocked to the floor. The molds are cooled down by bursting them open with a sledgehammer. This allows air to penetrate the molds, bringing the heat down a little. This step is essential for establishing the microstructure of the alloy, which directly influences its magnetic characteristics. After cooling, they shovel everything into a bin and salvage the magnet shapes using what else but a magnet. The molded pieces react like ordinary metal because they don't yet have magnetic power. So, it's time to magnetize them. These ring-shaped magnets, for example, are threaded onto a copper pipe. This ring-covered pipe is then placed in a much larger tube. It is then centered by packing silica sand tightly around it. The sand will hold the rings in position during the next step. After the tube has been sufficiently packed, its ends are sealed with concrete, allowing the inner copper tube to protrude slightly. Then it's into a different electrical furnace. It heats the tube full of magnet shapes until it's red hot. Heat treatment is a critical stage in the manufacturing process of magnets from alloys. This heat treatment is designed to optimize the magnetic properties of the alloy, enhancing its coercivity and remanence. The goal is to create a magnet with stable and reliable magnetic behavior. An electromagnetic coil, often shaped as a solenoid, cylindrical, is then used to mildly magnetize the ring metals. The coil is made of a conductive material, and when an electric current passes through it, a magnetic field is generated. The strength of the magnetic field is directly proportional to the magnitude of the current flowing through the coil. The material to be magnetized, which in this case is a bunch of ring magnets, is exposed to the strong magnetic field created by the coil. The alignment of magnetic domains within the material is influenced by the applied magnetic field. Once the process is complete, they break up the concrete seal. The process has left the ring shapes mildly magnetized, but most importantly, it's oriented the magnetic field properly. At this point, the magnets may undergo machining and grinding processes. Precision in shaping the magnet is vital for meeting the specifications required for its intended application. This stage ensures that the magnet aligns with industry standards and client requirements. The magnetization process is where the magnet acquires its magnetic properties. Even though it was subjected to a magnetic force before, that force didn't magnetize the material, it simply lined up the magnetic field. To turn it into a magnet, the piece is placed between the poles of a very powerful electromagnet and oriented in the desired direction of magnetization. The external magnetic field aligns the magnetic domains within the alloy, imparting a permanent magnetization to the material. The finished magnets undergo thorough quality control checks, magnetic property analysis, dimensional inspections, and visual assessments are conducted to ensure that the magnets meet industry standards and customer requirements. Researchers continue to search for even more powerful magnets than those available today. In the 21st century, a few countries are using powerful electromagnets to develop high-speed trains called maglev trains or magnetic levitation trains. These trains float over guideways using the basic principles of magnets to replace the old steel wheel and track trains. There's no rail friction to speak of, meaning these trains can hit speeds of more than 310 miles per hour. Yet high speed is just one major benefit of maglev trains. Because the trains rarely, if ever, touch the track, there's far less noise and vibration than typical earth-shaking trains. Less vibration and friction results in fewer mechanical breakdowns, meaning that maglev trains are less likely to encounter weather-related delays. This is just one of the applications of powerful magnets. Who knows what the future has in store for us? If you like this video and want to see more, check out our channel.